Okay, we are still moving ahead with differentiation. The big things I want you guys to see here is that differential calculus serves a great purpose in the sense of optimization. We talked a while back about quadratic optimization, but you cannot use quadratic optimization in every scenario. So the more universal method for solving optimization problems, whether it's finding a maximum or a minimum, is differential calculus. So for example, what I want you guys to see is if we look here at this function y equals f of x, whatever f of x happens to be. So it's going to be cubic. We know that just by the shape of the function, and we also know that it's positive because it's increasing. If it was negative, it would go the other direction. So the big things we want to look at here is we have a turning point here and we have another turning point here. If you notice a couple things, if you relate this to a sine diagram, on the left side of our first turning point, our function is increasing, so this is going to be positive. Between our two critical values, it is decreasing, so that's negative. And then to the right of our last critical value, it's going to be positive, increasing. So we can look and see already our signs alternate, so we should know that our factors are single factors. Now, how is differential calculus helpful in finding the maximum or the minimum? Well, if you would look at the gradient of the tangent to the curve at these two critical values, doesn't matter if it's maximum or minimum. What is the gradient? It's 0. So if we can take the gradient function and set it equal to 0, that's going to give us our optimization scenarios, such as the maximum or the minimum. Now, you notice here a pattern. If we are transitioning from positive to negative, like we are here, this first section, then we know that this creates a maximum turning point. If we're going from negative to positive, then we know that this creates a minimum turning point. So we should be able to figure out, based on the question, which solution are they wanting. So let's look at the next piece. You see a couple of different examples for quadratics or parabolas. And again, if you look at the function on the left side of the critical value, we are increasing, and then on the right-hand side we are decreasing, which tells us that this is a maximum turning point. And again, right here, the derivative or the gradient of the tangent at this point, point A, which is our maximum turning point, the gradient is going to be 0. Likewise, on the other side here, we have a quadratic, and we are transitioning from negative to positive about the critical value A, which tells us that this is a minimum turning point. And likewise here, the gradient of this tangent would also be 0. All right, let's look at a scenario. So we have a tin plate that's a 12 by 12 square, and what we're going to do is we're going to use some calculus here and optimization to try to find what is the maximum capacity of this ditch. And in other words, what size of squares should we cut out of the corner of this 12 by 12 tin plate in order to maximize the volume? So remember, volume equals length times width times height. So we've used this technique before. If we know that this is a 12 by 12 square and we're cutting out corners of x value, so then we could say that our length is, or excuse me, yes, our length of the base here, not up here, so scratch that out, is going to be 12 minus 2x. Likewise, since this is a square, the same value will occur for our width. So when we plug in our values, this is x. So when we plug in our value for the length, this is 12 minus 2x. We plug in our value for the width, it's also 12 minus 2x. Now, what is the height? We need to know the height. Well, if we take these flaps right here and we flip them up, these were squares. We are told that we cut out squares. So if this is x, then it's x all the way around, which means when I flip this up, it's going to be x in height. Now we can work this out, and this is going to give us 12 minus 2x squared. All of that times x. When we go ahead and expand, it's going to give us, I believe it will give us, yeah, it's going to give us 4x cubed. You can follow along with this thing right here. 4x cubed minus 48x squared plus 144x. Now at this point, we're ready to go ahead and take the derivative of this guy right here. So let's go ahead and do that. Remember, we're going to bump this down, which gives us 12x squared. We'll bump this down, which gives us 96x to the first, or just x. We'll also bump this down, which doesn't change our value. It's going to be 144, but it is going to affect this x because x to this, or any number to the 0 power is 1. So this would be 144 times 1, just 144. Cool thing is now we're at a quadratic, and it's convenient because all of these have a common factor of 12, which will make our a value 1, and hopefully we should be able to factor it. So let's go ahead and pull out this 12, which will give us x squared minus 8x plus 12. And then from here, I believe it will factor. So let's look and see. Yes, it does. So it's going to factor out to be x minus 2 times x minus 6. Now that we have the derivative, we're ready to take this thing and set it equal to 0. Why? Because the gradient of the tangent to the curve at either the maximum or the minimum, remember this thing. So here it is. So here's our tangent at the maximum. Here's our tangent at the minimum. Regardless, maximum or minimum, the gradient for each is going to be 0. So we set all of this equal to 0. Essentially now, we're just using the zero product property. So we can set x minus 2 equal to 0 and x minus 6 equal to 0. We're going to get the values 2 and 6 as our critical values. Let's make a sign diagram. So it's 2 and 6. Now, if we want to find out what's happening, aside from the fact that the picture is already here, we want to find out what's happening. We're going to pick a value that is on the left-hand side of 2, and we're going to plug it in and see what happens. So let's put 0 in. So we'll work that out, and we'll do 0 minus 2 gives us negative 2. Let's go ahead and multiply by 12, so it'll be negative 2 times 12. And we're plugging in 0 again, so this is times negative 6. And it's going to give us a positive. So essentially, it doesn't really matter to us what the value is. We just know it's positive. So this is positive. And we look, we know that these are single factors, just meaning that it's x minus 2 to the first times x minus 6 to the first. There is one of each, which tells us that we're going to be alternating signs. So we do positive here, negative, positive. Now remember I said if I'm going from positive to negative, this creates a maximum value, which is exactly what I was asked to find, the maximum value. So we're going to end up with something, this is a really bad drawing, but you get my point. So here it is, so there's our tangent, and the gradient of the tangent is going to be 0 at this point. So here's our maximum, which is 2. So we should cut out squares from this thing that are 2 centimeters by 2 centimeters in order to maximize the volume of this dish. Okay, now let's take a look at the next piece. So here's another example of optimization. If we have a business that employs X workers to manufacture furniture, then the profit made by the business is given by this function, negative 3x cubed plus 6084x minus 5000. So the first thing that we want to do here is we want to go ahead and try to find the derivative of this thing. So let's go ahead and work that out. So this gives us negative 9x squared. And this x is going to drop to 1. So this will just be plus 6084. And remember, all of our constants drop. So here's the derivative of the function. Now, when we want to find either maximum or a minimum, we're going to take that derivative and we're going to set it equal to 0. And the really cool thing is at this point that we don't have to factorize at all. We can actually just go ahead and solve for x. Now, the thing you want to be really careful about is pay attention, because all we're doing right now is we're finding the value of x at which this thing is going to be optimized. So let's do negative 9x squared equals negative 6084 divided by negative 9. Divide by negative 9. And we're going to get x equals the square root of 6084 over 9. And you can divide that out and see what you come out with, but you should come out with x equals 26. Now, this is all this thing is. This is the x value at which the maximum profit occurs. It is not the maximum profit. So at this point, we need to take our x value of 26, and we're going to plug it back in, not to the derivative. We're going to plug it back into the original equation. Negative 3 times 26 cubed plus 6084 times 26 minus, what is this, minus 5000. And from there, you should be able to go ahead and find that. When you work it out, you should come up with the same answer, $100,456. Now, this is your actual profit. Okay, one more we want to look at. Now, this is kind of similar. It should remind you of the truck and tunnel problem that you had on one of your recent tests or quizzes. I don't remember which. So let's take a look at how we work this one. The first question they want to know is, because we have a rectangle that sits on the x-axis, we're assuming it sits in the middle under the graph of this function, 9 minus x squared. Now, step one, don't overthink this, is they want to know what are the coordinates of the point P that lies on this function. So when we look at the x value, all they tell us is that the x value is x. So here's the first piece of our point. And then we know that our y value, again, don't overthink it, they already told us what our y value is. It's the function of x. So we take x and we plug it into this function, and it doesn't change. So our y value is 9 minus x squared as well. Okay, now the next piece is they want to know what is the area. So how are we going to find the area? Well, the length, or the width, whatever you want to call it, is x on one side and x on the other side, which makes it 2x. So area equals length times width. So for our length, let's plug in 2x. And we already said for our width is going to be our y value. It's going to be the same thing on, so that's 9 minus x squared. Now we can go ahead and work this out, and we're going to get 18x minus 2x cubed. From here, we can go ahead and take the derivative. So to end up with the derivative, let's So let's do this thing, and let's go ahead and reorder this so it looks a little cleaner. And so we take our 3 down and we get negative 6x squared. Take our 1 down, that will be 18 times 1 again, because this will be x to the 0, which is just 1. So here is our derivative, negative 6x squared plus 18. Now, this is not our maximum value. So at this point, we're going to take this thing, and we're going to set this equal to 0. All it is the derivative. Remember, when the derivative is 0, we have either a maximum or a minimum happening. So let's set it equal to 0, and we can just solve the same old way we've been doing these. Subtract 18, divide by negative 6, and take the square root. Technically, it's going to be both positive and negative. So here we go. But in this case, it's not going to really matter if we're using the positive or the negative. So our value is going to be technically positive or negative root 3. Again, this is not our maximum value. All this is x. It's the point at which the x value, or the value of x at which this occurs. So let's take this piece now, and let's plug it back in and see what we can come out with. So we're going to plug this thing in for the area as our value of x. So we end up with area equals 18 times root 3 minus 2 times root 3 cubed. Root 3 cubed is going to give us 3 root 3. Multiply that by negative 2 will give you negative 6 root 3. And so 18 root 3 minus 6 root 3, we can go ahead and work that out. That's 12 root 3. So this is the maximum area possible for this rectangle.